Okay, so welcome to this new session. In this session, we are going to discuss about Riemann integration. Okay, Riemann integration. Okay, so what basically is Riemann integration? Now, in your plus two level, you have studied integration in specifically in two sorts of consequences, right? One was it being simply treated as an antiderivative, that is the reverse process of taking a derivative of some function, and the other was, which was precisely called the notion of a definite integral, was as the area under a curve. Okay, fine. So this will be of more focus while treating the formal theoretical construction of an arbitrary integration. So let us serve a diagrammatic example of what we are basically the idea behind Riemann integration. So suppose this is A, this is B, we are in this closed interval, and suppose I have a function like this, for example, or let me take a bit simpler function in order to have a better understanding. Fine. Suppose this is a function I have. This is y is equals to f of x. Now the integration, what we are concerned about, at least from the point of view of your plus two level, was that integration of fx from a to b. It basically gave you this area, the area under the curve and the positive, or rather the x-axis. Fine. So what we are trying to do is that we are trying to formally define this integration. So we are ideating a formal definition of this notion, and this is basically the theory of Riemann integration. Okay, so Riemann integration basically deals with defining the notion of an integral of a bounded function. So we are concerned with a bounded function. Fine. And the theory is basically trying to approximate the area, which is area under the curve of that function, area under the graph of that function with x-axis typically. Fine. So how do I try to formally define it? To formally define it, what we need to do is to try and find the area under the curve, as I just said. But obviously, if you're given an arbitrary bounded function, the area under the curve can be anything, right? You cannot just look at the diagram of the curve and say that yeah, this is an area. Fine. To have a conceptually clear notion of the area, you need to approximate the basic area under the curve using some geometrical figures whose area is known to you, right? And the most elementary geometric figure whose area is extremely easily calculated is a rectangle, right? Fine. So what is the idea? So let me first talk about the idea, and then the definition is pretty easy. Okay, so the idea. Fine. What we do is, suppose this is one. So we will need two diagrams. What we try to do, we will be understanding with these two adjacent diagrams. So suppose this is A, this is B, this is A, this is B, and I have this curve. I have this curve. Fine. What I'm trying to do is that so the idea behind, as I already said, is just to try and approximate the area under the curve of this function. So this is my y is equals to f of x in both the cases. Fine. What I'm doing is that I'm trying to break the area under the curve into elementary geometric figures whose area is known to me. And as I said, that the most useful in this case will be a rectangle. So what I'm trying to do is that I'm trying to construct rectangles in this way. Okay, some arbitrary rectangles. Fine. Yeah, let's say in this way. Okay. So these rectangles. Fine. And similarly, I am again approximating rectangles. Now you can easily observe that these rectangles are slightly at a lower level than the curve. Fine. So the total area of all these rectangles will typically be less than the curve. Fine. Less than the area under the curve whatsoever it may be. Similarly, I can draw these rectangles being slightly larger than the curve given to us. Fine. right? In some way, like this. Clear? Fine. And in this case, we will see that the total area of all these rectangles, the way we will design it is approximately, or rather, I should say it in this way, is you know infinitesimally uh, more than the so-called area under the curve. Fine. And in this case, the total area of all these rectangles is infinitesimally uh, less than these curves. Fine. Clear? Now, what I try and do is that I take all possible such rectangles in either cases. Okay. So I go for all possible such constructions, that is breaking down the area under the curve into rectangles which are slightly lesser than the curve given to me. And in this case, we are also trying to do the same thing. So all possible such constructions, such rectangles which are having a total area slightly larger than the area under the curve. Okay, such constructions. Now, after doing that, if I take the maximum possible area here. Now, the maximum possible area will be, you will achieve the maximum possible area once these rectangles, the top level, I mean to say this part of the rectangle, these, okay, wait a minute, fine, okay, yeah, so these parts of the rectangles, they almost approximate the curve itself. Fine. Let me draw a picture again to make you understand this. So suppose, yeah, so this is what you have, A and B. Yeah, one second. Yeah, fine. So what I try to do is that I'm taking the maximum possible area of all these rectangles which are having their total area slightly less than the area under the so-called area under the curve. So for that I need to have rectangles smaller and smaller. You can easily observe that that is an automatic construction once we take the minimum possible area. Fine. And you can see that the rectangles have almost approximated the so-called area under the curve. Fine. The top part of these rectangles are almost the structure of the curve. And in a similar way, if I take the minimum possible total area of all these rectangles which are having their total area slightly larger than the so-called area under the curve, I need to construct the rectangles in a way that they are also very very close to the already given curve to us. Fine. Are you getting my point, what I'm trying to say? Fine. And the next immediate consequence you observe is that suppose you have achieved the maximum possible total area of all total area of all the rectangles you will be able to construct, which are initially having their total area slightly less than the so-called area under the curve to be, let's say, small m. And suppose this is the minimum possible total area of all such constructions, let it be capital M. If M is exactly equal to capital M, what does that mean? So that means that this area, the total area of these rectangles, is same as this area. Fine. Once this happens, that is, once again, let me draw it in pictures, you will be able to understand. So once this area is almost is same as this area, right? Then you can easily observe that them being equal, it eventually means that we can deal with this minimum value correspondingly this maximum value to be the area under the curve. Because once we have the minimum areas of all such constructions and the maximum areas of all such constructions to be same, then you can visualize it immediately that the rectangles can be thought of have been totalized in such a way that the total area of these rectangles is giving you the area under the curve. And in that case, what we eventually mean is that the rectangles have become in such a way that they have become the curve itself. The top part of these rectangles has become the curve itself. That is exactly what we have. If the minimum area of those constructions and the maximum area of those constructions are same. Are you getting my point? So that is the idea behind Riemann integration. So let's now formally define it. Fine. So the formal definition. Now when we will be dealing with the formal definition, we will keep on drawing the diagram in order to have a better understanding. Formal definition. Okay. So let f from closed interval a b to r be a bounded function. Be a bounded function. Fine. Let P be a partition a equals to x naught, which is less than x1, less than x2, so on and so forth, less than xn minus 1, less than xn is equals to b. Be a partition of closed interval a. What do I mean by that? So basically, by a partition we mean breaking down the closed interval AB into disjoint closed subintervals. So I have A here, I have B here, and I'm choosing this to be x0, I'm choosing this to be xn, and I'm having indices here x1, x2, x3, x4, and so on. Fine. I'm basically doing this. Getting my point? And so this is what we call a partition. Okay. So breaking down into small and small subintervals. That is exactly what a partition is. Typically. Fine. Now, fine. Now, let delta xi be defined to be the length of the subinterval xi. So this is just the length of the subinterval xi. Clear? So I am just talking about this length. So some subinterval, suppose this length. Clear? Okay. Next, fine. Let capital Mi be the supremum of the values of x when we are in the interval xi minus 1 to xi. Okay. We will come to the importance of these values. And Mi, small mi, be the infimum of the values of x when x is in the interval xi minus 1 to xi. Fine. Okay. So what are we trying to do here exactly? Let us understand this. So I have again two adjacent pictures. Fine. And this is my A, this is my B, this is a curve, this is A, this is B, this is my curve. I have broken down it into partitions, I have broken down it into partitions as well. Now, when suppose I am in this partition, this is my partition xi minus 1 to xi, the closed interval xi minus 1 to xi. So I am choosing the minimum value which f attains on this interval, and that can be graphically seen to be this. Fine. So in this case, I can consider this rectangle to be into consideration, and similarly all the rectangles are there. Okay, getting my point? Now the basic idea behind Riemann integration was to try and find the areas of each of these rectangles and add them up, typically, right? So to find the area of this rectangle, we need to have this length in hand and this width in hand. The width can easily be seen to be the length of the interval, and the length can easily be seen the values of f, the minimum value of f, which the minimum value which is attained by f on this interval, and that is exactly this small mi. Getting my point? Similarly, if I am in this interval, which is the closed interval xi minus 1 to xi, in this case, I am trying to take the supremum. So suppose I am considered about this value, right? So this is the rectangle which is slightly larger. As we are talking about during the motivation, this is slightly larger. So if I talk about the area of this, I need to again get hold of the width and the length. The width is again taken care of by the length of the interval. And for the length, I need the maximum value. You can easily see that this is the maximum value, the supremum of all those values which f attains on this interval xi minus 1 to xi. And that is taken care of by mi. Right? Therefore, if I, in this case, if I take mi times delta xi, I'll get the area of this rectangle. Similarly, if I take here small mi times delta xi, I'll get the area of this rectangle. And once I add them all up, I'll get the area of all these rectangles. Getting my point? Therefore, define UFP, which is called the upper sum, to be basically the sum of the, the total area of all the rectangles which approximate the curve from above. That is, the rectangles are slightly higher than the curve. These are called the rectangles which approximate the curve from above. So I is equals to 1 to n, capital Mi, delta xi. Fine. And similarly, we take the lower sum, which is the total area of all those rectangles which approximate the curve from below. Lower sum, this is summation, small mi, delta xi, I is equals to 1 to n. Fine. Clear? Now, as I said in the idea, that what I do, I take all such possible constructions, and for all such possible constructions, the only thing which needs to vary are these closed intervals. Because when we change these closed intervals, the rectangles will vary on their own. Fine? Because if you see that the idea of these rectangles are eventually come when we have broken down the closed interval AB into these smaller intervals, these smaller sub-intervals, right? Once we do that, so as we change these partitions, the eventual construction of these rectangles gets changed on their own, right? And the idea was that I need to take the collection of all such possible rectangles which approximate the curve from below and take the maximum possible area, total area of all these constructions, right? And similarly, I need to take all possible constructions of those rectangles which approximate the curve from above, and I need to take the area of total area, minimum total area of all such constructions, right? That is exactly the next thing which we do. So define, this is the notation ABF. This is called the lower Riemann integral to be the infimum of all the sorry, I need to take the maximum of all the constructions of the rectangles which approximate from below. So I need to take the supremum of all the lower sums as the partition varies. P over all possible partitions, because varying the partitions is equivalently varying these rectangles, right? Getting my idea? Possible partitions. Fine. And similarly, so this is what, this is the minimum possible to maximum possible total area of all those rectangles which approximate the curve from below. And then I have a b bar f. This is called the upper Riemann integral, which should be the minimum possible area of all those rectangles which approximate the curve from above. So it is the infimum of all these upper sums. Like P is partitions, P over all partitions. Clear? Right. So in other words, what we are doing is that we are taking a supremum of all possible such rectangles, which area of all possible such rectangles which approximate it from below, and infimum of all those possible rectangles which the total area of which approximates it from above. Fine. And then, as I said, that once these two values are equal, then we are good to go with the area under the curve. Define the integral of f. This is called the Riemann integral, or rather, let us not do it in this way. We state it in this way rather. We say f is Riemann integrable in closed interval AB, on closed interval AB, if there is a well-defined notion of area under the curve of f existing, right? As we said, this exists if and only if the lower Riemann integral is same as the upper Riemann integral. So f is said to be Riemann integrable on AB simply if the lower Riemann integral of f and the upper Riemann integral of f both exist and are equal to each other. In that case, we say that the integral from a to b f is exactly equal to this lower Riemann integral or the upper Riemann integral. Fine. And this is basically the definition of Riemann integral. Now there are multiple such integrals existing. For example, if you study Riemann integrals in great details, you will find that most of your calculus works which you have studied in your +2 level are more or less covered, rigorously covered using Riemann integrals. And the notion of it being taken to be an antiderivative will also be taken care of by the fundamental theorem of integral calculus. These are some other topics which are related to Riemann integration, and this is a very interesting and one of the most intriguing topics of real analysis, of a first course in real analysis. But there are multiple such constructions of integrals which are more and more general, for arbitrary functions. For example, there does exist functions which are not Riemann integrable. I'm not going to get into details of those, but there does exist such functions which are not Riemann integrable, but the geometric construction or the curve of those functions are such that they seem to have an area under it, or rather they seem to be integrable, but by the definition of a Riemann integration, they are not Riemann integrable. So there are multiple generalized integration theories. For example, the most intriguing one after Riemann integration is the Lebesgue integration. But this is quite a complicated topic because this completely deals with what we call measure theory, right? And there is one more way of generalizing Riemann integration while staying within the notion of Riemann integration is what we call the Riemann Stieltjes integral. I get this is the way of pronouncing it. Yeah, Riemann Stieltjes integral. So these are some general notions of Riemann integration. These might be covered in some other sessions, but this was all for this session. Thank you.